The first thing in section 16.2, which is also what the rest of this section basically hinges on, is what vector fields are. And vector fields basically are functions that would map a point to a vector. So you can have them in R2, where then you're going to take a point in R2, so just an xy, which would then get mapped to a two-dimensional vector, right? And you get the I and the j components there. And you can have the same thing in R3 where it extends the way that you would think it would. You have a point in 3 space, and then that gets mapped to a three-dimensional vector. You got the I, j, and k there. So then there are a couple of general pictures here where the idea, and I know these are a little bit grainy, and I don't know why this one's got a spotlight in the middle. I guess that was just the glare from the lamp or something. But you've got your point x, y, and then that gets mapped to this vector. And that's what all of these are. And then the same thing here is just that this one's three-dimensional. Right, there's your point x, y, z, and it's getting mapped to that f vector, whatever that is. Right, and then this point's getting mapped to this vector and so forth. To have one that's a little bit more concrete, here's a two-dimensional one where f of xy is negative yi plus xj. So there you can kind of pick the easier points and you can kind of see where everything goes. Like, even though there's no labeling on the axes here, like if you think of this point right here as being 1, 0, then what you should end up with for f is the vector j, right? 0i plus 1j. So then that should just go up 1. Right? Or then here you're at 0, 1. So then f, the vector that you get, should be negative I, right? Negative I plus 0j. So negative I would be 1 to the left. So like that. Right? So there you can see one. And I figured that was at least worth it to have one in there that was a little bit more concrete. But that's generally the idea, is that a vector field is a function. Even though when it's graphed, it doesn't necessarily look like what you would think a function would look like. It is a function that takes a point and maps it to a vector. One common vector field is the gradient field, which is derived from the idea of a gradient vector, which we had back in section 14.5, where you got your function f, then the gradient vector is basically just the vector of the partial derivatives. So if you do that, so just like the way that we would have gotten the gradient vector before, if you do that here, that will give you the gradient field. And if you look down here at this example where if that's my f, all I did to get the gradient field here is I just figured out what the gradient vector was. Right? I mean, if you look at these, you go, yeah, that's that 2xy, that's the partial with respect to x of f. Right? And then there's the partial with respect to y, and then there's the partial with respect to z, just that 1. And that's basically it. But then what does the gradient field do for you? Well, for any point that you want to pick that's within its domain, the gradient field will give you a vector pointed in the direction of the greatest increase of f. So that's the other part of this example. If you want a vector pointed in the direction of greatest increase for at the point 1, 1, 0, then you would just figure out what the gradient field is, and then you would substitute in. So since there's no z in here, you're just subbing in 1 for x and 1 for y, and you'd end up here. So you'd end up with 2i minus 2j plus k. So at that point, at 1, 1, 0, there's a vector pointing in the direction of greatest increase. So there's one thing you can get directly out of the gradient field, but that's sort of one common one that's not that hard to derive. The next thing is line integrals of vector fields, which if you think, well, technically is a function, so therefore it becomes a thing that we can integrate, right? And here this really uses that idea that the vector field is a function. So we've got our vector field f, where there's some m, n, and p functions of x, y, and z here that give us that vector field that are continuous, and then c is parameterized by r, just the same way it would have been in the last section, basically. Then also the parameterization would give you a direction, like that you would go from A to B, and that's the way that you would follow along the curve. So that generally would be considered the forward direction. And we need that concept in order for the next thing to make sense, which is the unit tangent vector. So there's another old concept, but the unit tangent vector is going to end up pointed in that direction. It's going to end up pointed in the forward direction. So the unit tangent vector is basically what it was before, right? Like this is an old definition here, right? The dr dt over the length of dr dt, or v over the length of v. This is kind of a new one, but this kind of also relates it to the last section. The unit tangent vector ends up being dr ds, where s is arc length, just like it was in 16.1. So you can write it that way as well. Any of those representations would be the unit tangent vector. And then how do you get the line integral of the vector field then? Well, what it ends up being, and this is another older thing where we had the tangential component and the normal component where we could break up vectors back when we were doing that, which now that's kind of a while back too. I mean, it would have been slightly after we talked about what unit tangent vectors were. But it's that concept kind of being brought in here, because what you end up doing is you end up figuring out the line integral of the tangential component of f. So how do you get the tangential component? It's the dot product of f with the unit tangent vector. So that's the thing that you end up integrating. So going along the curve, when you think about it, that makes sense, right? If you're following the curve, then at that point you've got a unit tangent vector, so whatever point that you're at, and then the dot product of that should orient you in the correct direction, especially considering that the parameterization should be set up in a way that you'd be facing the correct way instead of facing backwards. So that's essentially the idea. You end up integrating this thing. So then there are a few representations down here where it kind of starts off with this, and then it works its way up to the thing that you actually do. So yeah, it would be the dot product of f and t ds, but then you could rewrite t as dr ds, right? So that's this step. But then dr ds ds is just dr, but then we could rewrite dr as dr dt dt. And this is the one that you can actually do, because then dr dt, that's not too hard to get as long as you've got your parameterization of the curve already, right? As long as you've got r. And then you just rewrite f in terms of r. So instead of f being in terms of x, y, and z, you rewrite it using the parameterization, where if I go back and point at these for a second, like if you say, well, if that's x, that's y, that's z, then we can substitute in and have f written in terms of t, so in this dot product will give us something that we can actually integrate. That's basically what happens. So this one down here at the very end is the one that we're actually going to do. And that is the next thing. So kind of laid out in step-by-step form, we've got f, right? There's our vector field, and then there's our parameterization of c over here, the r. So the first thing you do is you rewrite f using the parameterization. And so basically you go to the parameterization, you say, okay, x is g of t, y is h of t, z is k of t. So we're going to sub in to these functions, whatever they are, and then we'll have f written in terms of t, or f written in terms of r of t. Then the other thing that you need is dr dt, which you should be able to get directly from here, right? Just taking the individual derivatives of g, h, and k. And then you can get the dot product and integrate it, and it's a definite integral from a to b, so the limits of the parameterization right there, and that should do it. So that's what we're going to end up doing. So this representation down here on the right side, that's the one that you actually end up using. That's the one that you actually evaluate. So if we go down here a little bit, we're supposed to evaluate the integral of f dot dr, and that's what f is right there. And then c is the twisted cubic, where there's its parameterization, ti plus t squared j plus t cubed k. And t goes from 0 to 1. All right. So then the first thing is we want to rewrite f. So notice what I end up doing here. I'm thinking x is t, y is t squared, z is t cubed. So the first function here, so the thing that's called m up above, that's just x times y. So there's x, there's y. Then here, y is t cubed, or what y is t squared, z is t cubed. So there are those. And then x times z, t times t cubed. We can simplify those a little bit and we end up here. So there's f of r of t, right? Now f is written in terms of t instead of x, y, and z. So that'll help later when we're actually going to integrate this thing. Then dr dt is just taking the derivative of this, right? And these are pretty easy derivatives, right? Derivative of t is 1, derivative of t squared is 2t, derivative of t cubed is 3t squared. And then we need the dot product of f and dr dt. So then, all right, t cubed times 1 right there. T to the 5th times 2t is right there. And then t to the 4th times 3t squared. If you simplify that, it's t cubed plus 5t to the 6th. And integrating that is not bad, right? We go down here. Then ultimately, this is what we were supposed to get, but we've rewritten it so everything's in terms of t. So we're going to integrate this. I forgot a dt right there, it looks like, but I guess that's okay. Then we're going from 0 to 1 since those are the limits of integration because they are the bounds on t up here in the parameterization. So then you integrate that and you end up here. And then there should also be a 0, 1 here. I got kind of sloppy with this one. And then that'll just be 1/4 plus 5/7, which would simplify to 27/28 if you get a common denominator. Another thing that's worth noting, because a lot of times what you end up having to integrate ultimately looks kind of like this down at the bottom. The derivation to get here is basically what the rest of this is. So this first part we already know, that the integral of f dot dr you can rewrite this way when everything's in terms of t. But then if you sub everything in, then, and this is one enormous looking integral, but this huge set of parentheses right here, this is just f of r of t, right? Where m now would be in terms of g of t, h of t, and k of t instead of x, y, and z. Same for n, and that should be a p, not an n right there. Then the dot product would be with r prime of t or dr dt, right? And then, I mean, that integral was so enormous that I said down here, I'm just going to write m, n, and p in shorthand. And you'd end up with m multiplied by g prime of t, n multiplied by h prime, p multiplied by k prime, which then you could break up as individual integrals if you wanted to. And the reason for doing that is that g prime of t dt is just dx. Because if x is g of t, then dx dt is g prime, or dx is g prime times dt. So this is written as three separate integrals to be able to say, oh, well, g prime of t dt is dx, h prime of t dt is dy, and then k prime of t dt is dz. And then conventionally, and this always bothered me for some reason, because I always felt like stuff was missing that's supposed to be there. But conventionally, this thing is written like this, where there's just the one integral symbol instead of the three integral symbols. So when you see this, it does mean that you've got to integrate the whole thing. And usually what happens is that you can write everything in terms of t, so you end up writing it as a single integral rather than three integrals. So I get it for that reason, but for, I don't know, it still feels that way to me, like there should be extra integral signs here. But when you see this thing, it does mean you got to integrate the entire expression. Then this example is just the same one as the last page, except that we're going to do this one using this formula right here. So this is one just to kind of show that it actually works. And then after that, we'll have an example that's actually set up for using this formula. So from what we had on the last page, that was f and that was r. So just taking what we've got with r, x is t, y is t squared, z is t cubed, right? Just pulling that directly out of the parameterization. But then if x is t, dx dt is 1, therefore dx is equal to dt. And then if y is t squared, dy dt is 2t, which would mean that dy is 2t dt, and then the same kind of thing for z, right? dz dt is 3t squared, so you end up here. Okay, well then for all of these individually, we should be able to just substitute in. So the integral of m dx, where m is xy, right? Because this is the m, right? There's the m, there's the n, there's the p. So m is xy. So okay, xy is t times t squared, and then dx is dt. So I just subbed in for everything. We've got our limits of integration. since t goes from 0 to 1 in the parameterization. So, okay, we can integrate t cubed. You get 1/4 t to the 4th. Evaluate it, you get 1/4. All right. We can do the other ones too, right? The integral of n dy, well, n is y times z, but y is t squared, z is t cubed. dy is that, right? Because that's what it is right up here. And then that's one where, again, the integration is not too crazy. And then integral of p dz, p is x times z. So there's x, there's z, there's dz, the 3t squared dt, because that's what it is right there. And I only put this dotted line in here because I wrote too close. Right? This line is too close to this. It should have had a bigger space in there. Then integrating that's also not too bad. It's 3/7. And you can tell, right? You're going to end up with 1/4 plus 5/7, which is exactly what we got last time. And yeah, you do end up with 27/28. So it does work. Individually, what those integrals are is that those are line integrals with respect to dx, dy, and dz. So now if you just look at them as individual pieces, then that is what they're going to be. Or that's a way you could kind of define what they are. And then the way that we're getting them here in these formulas, it's the same thing that's on the last page, right? It's that dx is the g prime of t dt, dy is h prime of t dt, and so forth, right? And then you just end up rewriting m and n and p in terms of the parameterization, right? That way everything's in terms of t, and doing a single integral would get you there, right? Because then you just have one variable that you're integrating with respect to. But then this example down here is one where it's set up to use those, right? Because we've got a piece where we're integrating with respect to x, we got a piece where we're integrating with respect to y, a piece where we're integrating with respect to z. And also the curve is in two pieces, right? We've got a line segment C1 and a line segment C2. So just like in section 16.1, you got to go piece by piece, right? You got to do C1 by itself, then you got to do C2 by itself. So for C1, we're supposed to go from 2, 0, 0 to 3, 4, 5. So then the vector that points in that direction, either written in the bracket notation or just 1 plus 4j plus 5k, right? Which we get just from subtracting, right? 3 minus 2, 4 minus 0, 5 minus 0. Okay, well then if we start at the initial point P, so the 2, 0, 0, to get the parameterization of that line. So you'd have 2 plus 1t, then 0 plus 4t, and 0 plus 5t, or just written like that. Where t goes from 0 to 1. Or if you want to write it using the r notation, it would look like this, right? So I've got x, y, and z just written separately, but you could write it this way, right? They're the same thing. That r of t is 2 plus t times I plus 4tj plus 5tk. Same thing. But I have them written separately just so I could get the dx, dy, and dz and have that look nice and clear cut. So dx dt is 1, so dx is dt, right? And then for y equals 4t, dy dt is 4, so dy is 4 dt. Similar kind of thing with dz, where you end up with 5 dt. And then here, if we're going to integrate this thing, it is just one integral ultimately. So right here, that notation I think does fit pretty well. Where then you say, okay, yeah, we're integrating this whole thing, but then there's, let's see, there's y, right, the 4t times dx, which is just dt. Then there's z, there's dy, and there's x, and there's dz. And so then this, we can combine some like terms here, right? So I just wrote it as this whole thing. We're going to integrate this all at once, and that ends up being 29t plus 10. So yeah, integrating, that's not a big deal, right? Integrate it, evaluate it, you get 49 halves or 24.5. And then we're going to have to do it with C2. So that's the vertical line segment from 345 to 340. The parameterization of that one's nice and simple. I guess you would basically do the same steps, but I was sort of running out of space. So I said, well, if you're going from 345 to 340, x is always just 3, y is always just 4, and z would end up being this, right? Because you've got to start at 5 and end up at 0, so it would be 5 minus 5t. If you want to do it with the vector, I guess the vector that you would get would be minus 5k. And then if you use the initial point of 3, 4, 5, then you're going to have 3 plus 0t, 4 plus 0t, and then 5 minus 5t. Right? So you end up there, or with the r notation, right, writing it out as a vector, you'd end up there. Well, let's see. Since x and y are constants, dx dt and dy dt are both 0, so therefore dx and dy are 0. But then dz dt is -5, so okay, for dz we actually get something. But then if we're going to do this integration, the only term that's not 0 is the last one. So then really we're just integrating that. And then x is 3, dz was -5 dt. All right, so that's -15 times the integral from 0 to 1 of dt. But that integral is just 1. So then that's -15. All right, so then the whole thing, so integrating with respect to c, so it would be the integral integrating over c1 plus then integrating over c2. So 49 halves minus 15, you get 19 halves or 9.5. This next example, this one's actually simpler than the last one, but I wanted to have one where it was set up this way, where it was just a line integral with respect to either dx, dy, or dz, because there are a few of those in the homework in the book. So we've got one that's just a dy, and I also wanted one where the parameterization didn't have t going from 0 to 1. And so this one checked both of those boxes, but this one is nice and short. So if we're going to parameterize c, so that part of the parabola that goes from -2, 4 to 1, 1, this is probably the easiest thing to do. I mean, you can make it so t goes from 0 to 1, but you're going to get a more complicated looking parameterization. Although you can have it if you really want it. But I think the easiest thing to do is just say, well, if y is x squared, just say, well, then if x is t, then y is t squared. But then we have to go from -2 to 1, right, to cover all of this. That's what the x values are doing, right? They're going from -2 up to 1. So that, I think, is the easiest thing here, right? Because then you can say, well, x is t, y is t squared. And the other thing that we're going to need, because we're going to have to sub in here, so we're going to have to sub in for x, we're going to have to sub in for y, we're also going to have to sub in for dy. So we're going to need dy, but if y is t squared, then dy is 2t dt. And then you can see the substitution down here. I started off with this, but then subbed in for x, subbed in for y, right, because t squared is t to the 4th, and then there's dy right there. And so then I pulled the 2 out front and then multiplied the t through. You end up here. Integration's not too bad. And then you just have to evaluate that from -2 to 1. And ultimately, what you end up with is 48, right? Because this subtracts out and gives you a 0. So really it's just the stuff that you're getting with the -2. And you end up with 48 ultimately. The back half of the notes, and I guess the back half of this section of the book, is applications of essentially what we were just doing. So finding the line integral of a vector field. The first one, which is to how to figure out the work done moving an object from one point to another. If you look at the integration, it's the exact thing that we were just doing. So if now F is a vector field that represents force throughout a region in space, so something like gravity or an electromagnetic force, I guess those are the easy ones, but something like that, right? So we still just have some vector field F, but now it's supposed to represent something, right? So there's the applied part. Now it's a force throughout some region in space and a curve parameterized by R. Then the work done moving an object from basically the beginning of the curve to the end of the curve, right? Because that's the beginning and that's the end. It's what we're just doing. So the work, it's the integral of the dot product of f with the unit tangent vector, ds. Then we already know how to rewrite this so we can do it where everything's in terms of t and we got the definite integral. And so that's exactly what you do. So what happens in this example, other than the fact that it's about the amount of work being done, it's the exact same thing that we were just doing. So now if this F, so that's a force field rather than just some generical vector field, but I mean, it is a vector field still. Moving a particle along the quarter circle, I guess of the unit circle from 0 to pi over 2. Okay, well then we know what x and y are from R, right? X is cosine t, y is sine t. Okay, so we can substitute in. So f of r of t, so there's x squared, there's x times y. And then dr dt, right, just a couple of trig derivatives from up there. So then f of r of t dotted with dr dt will end up being this. So minus sine t cosine squared t minus another sine t cosine squared t. So that's minus 2 sine t cosine squared t. And then for the work, we're just going to integrate that from 0 to pi over 2, right? Because those are the limits on t up there. And that's not too bad, right? You can bring the 2 out front if you want to, and then that becomes a u substitution where u is cosine t, because then du is going to be negative sine t dt, right? So you integrate that, you get 1/3 cosine cubed t, and then that's multiplied by 2, which is how I'm getting that 2/3 there. But then if you figure that out, then it's going to be 2/3 times 0 minus 1, which is just negative 2/3. And then there is another thing that's worth pointing out, that if you go the opposite way, you would get the negative. And I guess with the integration, you can see that right away, because you go, well, yeah, if you go the opposite way, then the limits of integration just reverse. You have a pi over 2 down there and a 0 up there. And so then you would ultimately end up with the negation of this. So you get positive 2/3. Yeah. That's what's supposed to happen in terms of integration, right? But that's also supposed to happen from another perspective, which is that if you're going in the opposite way, then the unit tangent vector points the opposite way. And so therefore, ultimately you should get the negative of what you got in whatever the original direction was, if then you go in the opposite direction. So that's another way that you could look at that. And certainly that would be true just from an integration standpoint. But I guess the theory behind it would be that the unit tangent vector points in the opposite way. So therefore you should end up with the negation. The next thing is flow and circulation. And if you just look at the integral, you go, wait, it's the same one again. And it is. So now, instead of being some kind of force field, what if F is a velocity field of some fluid? Then if you integrate the dot product of F and T along some curve C, that would give you the fluid's flow along that curve. Or if the curve starts and ends at the same point, it would be circulation. That's the only difference between flow and circulation. Really, a circulation is just a specific kind of flow, right? It's one where the start and end points are the same. And then generally for flow, that doesn't have to be the case. But the way that you would do the computation to get flow, if you're looking at this, you're like, this is the exact same thing as work, right? Identical, right? We're going from R of A to R of B, and you go, yeah, it's this same exact integral. And it is, or it's just a different context, but it's the exact same thing as far as the math goes. So going down here, I have one set up just for flow in general, which is not a circulation one because you don't start and stop at the same point. But then in B you do. So this one would be circulation. Because really, if you look at what this is, it's just a unit circle raised up by 1. Right? Like it's a unit circle in the XY plane, but then moved up 1 unit, and Z. So yeah, that one you start and end in the same place. So B is going to be circulation. But with A, I guess the first thing is we're going to substitute in, right? So if you look at the R that's right here, you go, okay, there's X, there's Y, there's Z. So then subbing in, you end up here. And then the derivative of R, so R prime or dr dt, ends up being that. So then if we get the dot product, cosine squared plus sine squared minus t, but then really that's just 1 minus t using a trig identity. But integrating, that's pretty easy. So integrate that and then 0 to pi, because those are our limits up there. And you end up with pi minus 1/2 pi squared. Okay, then the circulation one. So the only difference is I basically just got rid of the t that was right there. And then it goes to 2 pi, so you do end up in the same spot that you started in. But yeah, then f of r of t would be that. R prime is this, because now, since there's no t anymore, right, you take the derivative of 1, you get 0, so there is no k component there. And then the dot product, you just end up with a 1. And okay, you integrate 1 from 0 to 2 pi, you get 2 pi, right? So that's the circulation. which makes sense for what that is, right? You're just going around a unit circle once. So, okay, sure, that's the circulation there. But yeah, the difference between circulation and flow, it's just that with circulation you start and stop at the same point. The next application is flux, but we need a little bit leading up to it because part of the definition involves the idea of a simple closed curve. So just to kind of run through what these are. So a simple curve doesn't cross over itself or intersect itself. And then a closed curve starts and ends at the same point. Or I guess to look at it another way, it's a loop. So, right, like this one's a loop and then the third one's a loop. Right, so those are the two that are closed. Right, this is not closed because it's clearly not starting and ending at the same point. And then neither is that one, so that's not closed. But then the first two are simple because they don't overlap themselves anywhere. But then this does, right? It's a figure eight, so that's not simple. And then this also goes over itself right there, so that one's not simple. And that's the basic idea. So for what we're going to do next with flux, it's got to be this one. So simple and closed. And if we go down to where the flux stuff is, so now if C is a smooth, simple closed curve, right? So there it is, simple closed curve. And N is the normal vector pointing out rather than pointing inward, then, right, because if it's a smooth, simple closed curve, right, you've got something like this that's a closed loop. So pointing out is like that, right? Pointing in is, I guess, in toward the inner region enclosed by that curve. So pointing out, right, like that idea makes sense when you have a simple closed curve. Then what the flux is going to be, notice it's a little bit different this time. It's not f dot t, now it's f dot n. So flux is actually different from the way that you would get work or the way that you would get flow by integrating. So you've got the dot product with n instead of with t. So then for counterclockwise motion, n ends up being t crossed with k, at least motion in the plane. So then I guess that would imply that we're just in the xy plane, right? Which is what we're getting here with the I and the j. That would be the conventional way of doing it. I should have said that at the beginning. But okay, fine. If n is t crossed with k, then the dot product of f and n should be this, right? Because then the m and the n are coming out of f. And so then how you would get the flux? Well, you would integrate this, basically. So you end up here, and then the notation is a little bit different. I couldn't get it to look the way it's really supposed to, because that circle that's in the middle of the integral sign is supposed to have like a little arrowhead on it to indicate that we're going in the counterclockwise direction. So then that's the way the arrowhead's supposed to point. And that's just there to emphasize that that's the direction that the integration is happening in. Our book has it, like it has the arrow. I couldn't really make it in Word. That's not possible. So that's why that's not there. But that's why there's this sort of, this paragraph here about it. Because that notation is supposed to look slightly different, but I couldn't make it that way in Word. I couldn't have the directed circle. I could just have a regular circle in the middle. And then you can have clockwise motion too. We're just going to focus on counterclockwise, but for clockwise motion, n ends up being k crossed t. So, right, you get the cross product in the opposite order. So you can have it, but for right now, we're just not going to worry about that. We're just going to worry about counterclockwise. So for this last example, it's going to have to be one where we find the flux. And that's exactly what we're going to do. We're going to find the flux of this F across C, where C is the circle of radius 2. Okay, and centered at the origin. All right, so first things first, we got to parameterize C. Basically, you end up just sort of rewriting in polar coordinates, right? Where you say, well, then x would have to be 2 cosine t, y is 2 sine t, and then if t goes from 0 to 2 pi, that'll get us all the way around, right? Then that'll give us the simple closed curve, right? And from t equals 0 to t equals 2 pi, that's counterclockwise, right? So there are other ways that you could set this up, but that's going to be the simplest. Right, we've got the counterclockwise motion, we got a simple closed curve, so it looks like we're all set. And then looking up here at f, m is y and then n is x plus y. So we can rewrite those, right? So y is 2 sine t, x plus y is going to be that. And then if y is 2 sine t, then dy would be 2 cosine t dt. And then dx is going to be negative 2 sine t dt. And I wrote these where they are just because then these get multiplied together and then these get multiplied together down here in this next step, right? Because then we're going to integrate counterclockwise over c of m dy minus n dx. So let's see, there's m dy. I guess I went ahead and stuck the dt down at the end, but then right there's the dy part except for the dt since it's included down there. And then minus n, which is right there, times dx, which is right there. All right, well, we got to simplify this a little bit. Right, so, all right, we can simplify all those from here, right? I guess this is just some multiplication and things. And then you go, we can combine like terms, there's that. And then I broke it up into two separate integrals because that first one is just going to be 0, right? Because that's a u substitution where u is sine. So you get, all right, 1/2 sine squared, but then sine of 2 pi and sine of 0, those are both 0. So this whole thing's going to 0, which is right over there. And then you got to use that trig identity again for the integral of sine squared t, right? So there's sine squared t rewritten. And then, let's see, I brought the 1/2 out front, so then 4 times 1/2 would be 2. And then integrating that's not too bad. And then evaluating from 0 to 2 pi. The only term that's going to give you anything is when you put the 2 pi in for t. So that's 2 times 2 pi, which is 4 pi. Okay, so integration's not terrible, right? Like once you got everything set up. And then what does this tell you? Well, in this example, we have a positive number, right? We ended up with 4 pi. And generally when you get positive flux, that's when you have a net outward flow across C. And then negative flux by contrast, which isn't happening here, but I figured if I was going to write the first part, I should write the second part. The negative flux, that would tell you that you have a net inward flow across C. So this example, positive flux, so net outward flow across the circle of radius 2 centered at the origin going counterclockwise.